Hello, this is Silvia Mazzoni, and in this video I'm going to show you how to run a ground motion analysis in eSEES using eSEES, a graphical and scripting user interface for eSEES. I'm going to start a new file. I'm going to call it ground motion example. Oh look, I've already done one before. No problem, I can just overwrite it. This is a window that pops up when the program wants to communicate with you. Every time it runs something and it needs to communicate, even something that works, it's going to generate this window. What I recommend you do is either move it over to your next screen if you have one so that you can keep an eye on it, or minimize it. So I'm going to take it and move it over to my next screen. To get started, I look at my file setup. I'm always happy with the defaults because after all I did set them. And let's make this interesting and let's do a reinforced concrete section. So we have to define the materials. Here's a confined concrete material, 4 KSI. I like all the defaults. I'm going to save it, and when I save it, it actually runs an eSEES analysis and shows me what it looks like. I'm happy with that. Then I'm going to define an unconfined concrete. So I'm going to go to concrete, unconfined concrete, same value. Maybe I'll do 3,500 PSI concrete. And I'm going to save it. It's going to test it and show me what the behavior looks like. Excellent. Let's define the reinforcing steel. I like these degrading models. And here's the input. You've got the required and the optional input. What I'm going to do for the required input is I'm actually going to just load up the sample values. I'm happy with these. They're for standard 60 KSI steel. You can always go in and change these. If you want to know what these different parameters represent, you can click here. It takes you to the eSEES wiki manual about this material. If we go back to the program, I'm going to extend the strain range to see what it looks like. I'm happy with it. There's a point where it starts degrading in strength or losing strength on the envelope. And what I like to do with this material is scroll down to deterioration parameter. What this controls is the overall envelope deterioration. A lot of other parameters are there that I'm not very familiar with. I like this parameter because it does pretty much what I wanted to do, which is just cyclic degradation of not just the in cycle, but also the envelope has degraded. It's a pretty large amount here of degradation. I kind of want to have a strong effect, so I'm going to keep this value. What you want to do is play with this value until you achieve what you see in your tests. And I'm going to actually call this steel, and I'm going to save it. Now let's build the reinforced concrete section. I'm going to do a rectangular section that's not symmetric, so it'll be more interesting in the two directions. So I'm going to go here, RC rectangular fiber component, and I'm going to say, let's make it 30 by 48. Nice different aspect ratio. The cover material is going to be the unconfined concrete. Core is going to be confined concrete, and then I'm going to put steel for the reinforcement. Once you've defined the required arguments, you do see a display of your cross section. So if you want, we can actually test it, and we see that this is pure concrete and it doesn't have a lot of bending strength. So let's add some reinforcement to here. You've got the options for the bars at the top, so let's put a few bars at the top. Let's make them number 11 bars. We can add a second layer to those. You can control the spacing of the second layer, but I'm happy with the default for now. I'm going to put some bars at the bottom. Let's make it an anti-symmetric. So let's see what this looks like. Behavior. There it is. It's very anti-symmetric. I'm going to save this as the beam. So let's go here, and we're going to call this a beam, and it's saved. Now what we're going to do is just to kind of make things a little bit easier, more interesting, we're going to use the same cross section. And I'm going to make the columns. So I'm going to put in some intermediate reinforcement on the sides, but here's my side bars. So now if I test this in bending, I have a little bit more symmetry because I've added all these bars. So let's take a few bars off. Okay, let's test that. So we have still an unsymmetric section. And then if I test it in the other direction, it's definitely a different strength. Let's see if I copy this moment curvature data and I paste it into the regular section about the bending, strong bending axis, you see that we do have different behavior. And I'm happy with this. And so now I'm going to save this as the column. Save it. I'm all done defining my materials and my cross sections. So now let's define an elevation. I don't need element types for now. Let's go over to elevations. I'll go back and define the ground motion loads, but I kind of like building the model first. We're going to make this be a 5-story frame. You could do almost just a single column, but just to make it more interesting. So I'm going to turn off the diagonal braces and the beams. I'm going to select my column cross section. Okay, and I've got same as node I for both the middle of the section and the other end. So I'm happy with this. You have to be really careful with that because they're going to get changed. Let's turn off the beams. So I'm only defining sections. With my shift key, I choose all the columns. Yes, I'm happy with those. And there they are. Now I want to define the beams, so I can turn off the columns, but I don't care. I'm done with that. Let's go to the beam cross section here. And now you've got to make sure that the other points are also beams. So you actually can define 3 different cross sections along the length of the element, even if you have more integration points here. Now I've got the beams, so I'm going to shift and select all these beams. Yes, I want to select these. Perfect. Done with the model. Let's define the gravity loads on it. I'm going to say I have a distributed load of maybe 12 something kips per. I have a tributary width of 1, so this is per area or per linear inch because I have inches as my basic units. So I'm going to assign this to this floor. I'm actually just going to design it to all of them, and then I'm going to change this to actually be half of that. Okay, change my properties. I would like to be 180 here, and this is going to be actually a wide portal frame. Okay, this is what it looks like. I'm happy with my elevation. Now I'm going to define a grid, new. Yes, save it. Remember, when you're dealing with a model, it's always going to ask that, just as a reminder to make sure you save it, because as soon as you pull out, it loses everything that you have done. So I'm going to go to a grid. Now my grid, I'm going to make it not symmetric. This is where, for the 3D model, you define your bay width. So you can have one elevation with different geometries. So in this direction, we're going to make this be 240. And I'm going to actually reduce this. And I'm happy with this. Save it. Let's build my 3D model right away. Yes, I've already done the saving. I'm going to do a 3D frame. I'm going to pull out my grid. I've only defined one elevation anyways. I want to turn off my rigid diaphragms just to make it interesting. Number of modes. I didn't change the number of modes in the elevation. I'm going to go and change that. Here I've got 1, 2, 3, 4, 5. So I definitely have, let's just, be able to look at 8 modes here. It doesn't really matter anyways. So I'm going to save it here. And I can't really save it because I haven't assigned anything. So let's assign some framing to here. There's my structure, and I'm going to save it. Actually, I'm not going to save as. I'm just going to overwrite what I had before. And now I'm happy. You got to be careful because somehow the rigid floor switch got turned off. So I'm going to turn this off and modify and save. So that's a default that I need to check. Then I'm happy with all my models. This is where it gets interesting. Let's define our loads. I want to do a ground motion first for the 1D. So I've got a uniform earthquake. This is I'm going to call this earthquake 1D. I'm going to go and find the ground motion for that. And it's going to be somewhere in my folders. I believe I have a ground motion file here. And here's my one direction. I'm going to save this. Then for the 2D, you can just subject it to a single one of these motions, but let's put a bidirectional loading. So I'm going to go with this load here, the 2D, and then I'm going to go back to my folder and choose this one. Maybe I'll copy this path. Choose this one here, and then here. I'm going to paste the path that I copied before, and here it is. So I've got the two directions in the X and in the Z. You could switch the files if you want, but I'm happy with this. As you'll see the options, this is the PRNGA West 2 format. If I click view, it's going to go and open and plot it to make sure that it's read properly. Yes, there's one. And there's the other. I'm not going to worry about the scaling here because I'm actually going to do the scaling in the load combination. So I'm going to save this load also, and it's called Uniform Earthquake 2D, which is fine. Now let's do the load combinations. I'm going to do a new load combination, and this is going to be in, I'm going to call this Earthquake in 1D, and I'm going to first apply gravity, and that's the static analysis part, and then the transit analysis part, I am going to do the 1D earthquake. And I'm going to put it in the X direction for this case, and then let's scale it maybe by 5. You really want to be careful with your scaling because maybe it's too high. And then for damping, I am going to do Rayleigh damping of 5% for modes 1 and 3, and I'm happy with that. That's my 1D. Then I'm going to do the 2D, and I'm just going to modify this. So I'm going to change the name before I forget. Now let's remove this transient. It's asking me, are you sure? Yes. I'm going to keep the gravity there as it is, and I'm going to add transient analysis, the 2D. And now I can scale the two directions separately, but I'm just going to do a scale factor of 5 on both of them. It's always a good thing. A mass and stiffness or proportional damping, and again I'm going to do modes 1 and 3, and then I'm done. There it is. I'm going to save my model. Now I'm ready to do the analyses. So let's run some analyses. Let's first deal with the, look at both of them, and let's look at the mode shapes. Oh, I have to pick a load combination because mode shapes are dependent on mass. And mass is associated with the load. So let's do these under gravity only because all other cases still are controlled by this gravity. So let's display the modes. And maybe since they're higher degrees of freedom, I'm pretty sure we can go all the way to 5 modes for the 2D model. So as you can see, even in gravity, I've got some convergence issues. But once it's applied gravity, then it's going to perform an eigenvalue analysis. And here are my 5 different modes. It's actually consistent with what I'm expecting. I believe this is probably axial, that it's hard to see it here. And I'm happy with this. And go find your window and you press enter. Now it's going to go to the 3D model. Applying gravity. You can see the OpenSees analysis is trying to run. Maybe I should define a better section, or maybe my loads were too high. I've got my periods. And you can see now you've got 1, 2, 3, 4, and 5 modes, and these are displayed in 3D, so these are the 3 different planes and a perspective. These are generated by OpenSees, which I kind of like because then I know exactly what this looks like. And as you can see in this figure here, which is the plan view, the fact that I don't have rigid diaphragms brings in this mode here, which is pretty much the 2 flanges are flapping in and out. So it's interesting to just kind of see what these mode shapes look like. But I'm going to press enter and I'm going to exit. I'm done with those. So now let's go back, pick only the 2D model, and let's run the 1D uniform earthquake motion. Analyze it, it turns on and goes to OpenSees, and it's actually running the analysis at this point. You can visualize the deformed shape in this large figure, and then the smaller plot is the force deformation. You always see something strange at the beginning. That's the gravity load being applied. And now you can actually plot. Time is in the vertical axes, and the displacement at the master node, typically it's at the top node in this case, is being plotted in the horizontal axes. It's done running the analysis. It probably may even have run into a problem. Let's see. It's done analyzing. This is when you pull out the little window here. You bring it over and it tells you what OpenSees did. And it actually had a problem in the analysis, which is great because this is what I wanted to demonstrate, that you can get the output from OpenSees. Well, let's look at the results here, what's going on. And it's really hard to tell when you've got these types of problems, but if we go to this maximum displacement and we plot our bending moment diagrams, I'm going to scale it up a little bit. It's really hard to tell what actually happened. So what I'm going to do is I'm actually going to pick this column here. Maybe I'll look at the rotations. Curvatures, actually. And where are my largest curvatures? They're actually in the beam, I believe. So I've got this diagram here that's like a colored diagram. And if you scroll this little guy here, it selects only the elements that are higher. And so this beam here is subjected to some really large curvatures, and you can look at your cross section, see if you learned something from it. Let's look at the unconfined concrete. Let's look at the 4 different corners. But sometimes these convergence issues are just because of you've reached that maximum limit, but not just at a section level, but at overall system level. Here's what the steel looks like, and yes, we've reached a plateau. So we've actually formed a hinge in this beam enough that it's having convergence issues. So that's really helpful to actually see what's going on. If you want, you can even plot a moment curvature relationship here, MZ versus phi to see what was happening. And yeah, we've reached really large curvatures in that beam. So, but I think this is enough to show you, to demonstrate what we've done in the analysis. Let's go play with a different model. Let's play with the 3D model and apply a uniform excitation in the 2 directions. I'm pretty sure I'm going to have problems with this, but let's see what happens anyways. Here's my analysis running. Now you've got the 3 planes and a 3D perspective. This is actually being generated by OpenSees. And then in the 2 diagrams, you can see the displacements in the X and in the Z. It takes a little bit of time for the program to actually generate the output, and I think it's actually running the analysis right now and struggling, and that's why it's not really plotting anything. So it's gotten through gravity at this point, and now it's starting to move. I really don't know how far it's going to go. You can see the deformations in the 2 directions, as well as this planar view here. The 3D frame is doing a much better job with the earthquake ground motions. But let's see how far it's able to go. We did scale these 5 times. It's made it that far and ran into problems. Let's see what it gives us from the OpenSees output. Now you'll notice here it's taking a little bit. It still says analyze here. So there's a lot of work that goes on in the background of actually processing the analysis. Sometimes the post-processing takes longer than the analysis itself. So we make sure we scroll this to the end, make sure we're looking at the proper model, that we're not looking at the old analysis. So I like to scroll all the way to the top and look, okay, what load case am I looking at? I'm looking at the 3D frame in the earthquake 2D. It gives you the header of the ground motion file that we read. It's kind of good to kind of check. And this is the output. It gives you some information. This is the output that OpenSees is giving you. Yes, it's had some convergence issues even before we got through gravity. Made it through gravity. No, we didn't. We didn't manage to apply the entire gravity load. It did manage to compute the eigenvalues, but remember, it's really all it needs is the mass, but it is at this point in the stiffness. So you have to go back and check your your cross sections and your model. This is something I just made up on the spot, so it's understandable that it's not fully working. And here's all the output from OpenSEES. If we look at the results, as you can see, it didn't make it very far in the analysis. You want to give this a little bit of time to load everything up. It looks like everything is loaded. Here I'm plotting the curvatures. Let's look at the bending moment diagram. I like it on the tension side. And this is just at gravity pretty much. Let's go to our maximum displacement. So this is the maximum displacement in the X, I believe. This is in the Z. And this is in the Y, the vertical displacement. So there's definitely even some displacements in the vertical direction. This is just of a reference node at the top floor. What we want to find out is what's going on at our element level. Oh, look at that. Look at our concrete. It actually went through a full cycle here. Let's pick a fiber. So maybe this corner over here and this corner over here. Let's look at the very unconfined concrete on the outside. Let's look at the confined concrete on the inside. There's a lot of tension there. And maybe if we look at the other node, so this is at node J. Now, what we could do is we can plot the moment curvature response of this element as a function of time. And maybe the best thing to do is, and I'm just going to set these windows aside, is let's look at the curvatures, because the curvature really gives you a good measure of deformation. So here's my curvature in the Z direction. And then I'm going to pick this point in time, okay, which is our maximum point. And as you can see, we have significant deformations and curvatures. And I'm trying to figure out, okay, which is the critical element? So I'm going to move this here. And once again, it's this beam right here. I could see it. So let's look at the fiber response here. And we've definitely pushed our concrete to the limit. Let's even look at the steel. The steel is subjected to some pretty large deformations. It actually only managed to load in one direction. Sometimes if you use a different material, maybe you could use the hysteretic material instead of this material, you may actually get a different response and may be able to actually go further. But here's the cause of our problem is our reinforcement has actually reached the point of zero tangent. This is the limit to this material type. And therefore, this is definitely going to give you some convergence issues. So this is why we found out is what's going on with our section. So maybe all we have to do is redesign that beam or come up with something more realistic. Now, what I want to do is I want to show you the OpenSEES files. So I'm going to go in and pull out the input file that was generated by this model. So here I am in the data. This was my root folder where the executable was. And therefore, I went into the data file, and these are just the many data files that I have run. The latest one is this ground motion example. And here's a bunch of different files for different load cases that I have run. It saves them every time in here. And these are the actual OpenSEES input file. And this is the log file that is generated by OpenSEES. And then within these folders, you go by model. So let's look at the elevation while we subject the elevation to the 1D and the default gravity. And then there's some additional data for your model. So what I want to do is let's look at that model. The elevation is the simplest one. The OpenSEES input file for it. Here's the input file that was generated by eSEES. It's an OpenSEES input file with a lot of different parameters. Here's our nodes, our boundary conditions, our materials, our fiber cross sections, the data, the definition of the element, the recorders, the gravity load pattern, the nodal masses. Here's the analysis process for the gravity load. And then this is where it's computing the periods. Now we're going to go into the transient analysis. And this is where the program itself has generated for you a load pattern and the time series. It gives you the directory, the file type, and then here we are, we're defining a time series. with the file path that is given here, which we look up, and it's given actually up at the very top of your input model. And the factor that we're putting in and multiplying it by g automatically, and the phi was the scale factor you wanted. And now the uniform excitation load pattern takes this time series and uses it as the acceleration time series. It's a simple analysis, and so that's how that is defined. And then the rest defines the damping, and these are actually all the different steps and process for convergence for your transient analysis. And that's pretty much it. Thank you. Bye-bye.